Hello everyone, welcome to the EasyPower Refresher webinar series. My name is Jim Chastain, an applications engineer here at EasyPower, and today is the fourth installment of our four-part series we call Introduction to Protected Device Coordination. Today with the emphasis will be on relays and ground fault protection. Very much appreciate everyone attending today. And as we are in the habit of doing, we like to start off today's session with poll questions. And today's questions center around the topic. And the first is, how often do your projects include high resistance grounding in the system, or at least neutral resistant grounding in the system? Again, we do appreciate your attendance. There's no obligation to the poll, strictly trying to get some feedback from the audience and hopefully being able to direct the conversation in the presentation to the preferences that are shown. So it looks like we have close to a quorum on this question. Here's how folks have weighed in on it. Very interesting. Thank you very much. And then the second question is, how often do your projects include arc flash sensing relays, light sensing driven relays that are installed in areas that we want arc flash protection? And again, this is a relatively new technology, which can be retrofit, but I'm curious how often people have run into it. And again, we're not talking so much about arc flash today, but there is a crossover, I think, in a lot of these topics. So it looks like we have a quorum here. Here's how folks have weighed in on it. Also very interesting. Thank you for participating. Okay, so I want to emphasize that this is not an in-depth, thorough analysis of any particular topic. It's primarily leaning towards the utilization of the tools and how to extract or derive the information that's required for certain functionality. So my apologies in advance if I misappropriate some parts of the code, but hopefully you'll be able to bear with me. We're going to try to cover transformer protection in some amount of detail, talk a little bit about grounding systems, and then get into some examples, and in some cases show the specific advantages that EasyPower has in this particular field. I think we all can agree on the definition of coordination and the purpose of it. And for the most part, relays are the element that ties the system together. And there is a limit. One of the details, or one of the drawbacks of especially instantaneous tripping, is that it makes the situation more difficult as far as coordination. So the places where instantaneous tripping is recommended or most useful is directly above the load that we're concerned about, and then at the very top part of the system where we know there's a certain limit that we don't want to exceed. So we're going to be talking about that as far as relay protecting the primary transformer. There's two primary standards in the ANSI world to describe liquid-filled and dry transformers, the definitions and the guidance as far as the guidelines to protect against that damage. And the type of faults that are of most concern are both internal and then through faults. The internal fault is something we really can't directly monitor from the system details. And so all the protection that we're going to be talking about is primarily for through faults, which occur downstream of the transformer secondary. Now we will get into the differential relays, which are basically gold standard for transformer protection because of their ability to measure relatively small differences between the input and the output, or the expected output of the relays, the transformers. And just a side note, although this applies more to arc flash, question comes up is regarding the fuse protection, usually on the internal workings of the transformer, and how does it affect arc flash? Primarily, those fusing, or that fusing, is to prevent fires or mechanical damage of the transformer as a whole, and so it doesn't affect the arc flash calculations that are derived from the protective devices we're going to be describing. So the key elements, the key points as far as transformer protection that we're looking to analyze or support is the full load current, and that's the maximum load current under normal operations. And it's defined by any National Electric Code recommendations. And so primary protection can be set between a number just slightly above that full load current and then some maximum current under a full-blown fault, secondary fault. The fact that we can predict what the maximum current is at the primary for a secondary fault gives us the ability to have a limit, if you will. And so in the NEC, we'll see that there's a max recommendation for that number. Now these limits or recommendations are built into the EasyPower help section, and very often the protection recommendation is to set the protective devices 200% above the inrush, which again is calculated and plotted on the TCC curves. So as a whole, we're looking for through fault protection, and that's described in the description of both oil-filled or liquid-filled and dry transformers as the upper portion of the curve, which is lower current but longer exposure, and then the mechanical damage, which is literally the impulse reaction of high current, which will physically force the windings apart because of the inductive reaction. So these are all part of the TCC plots, and we described basically what those plots look like in the first part of this series. Now again, we have the ability now, if we know the maximum through fault current, of utilizing the instantaneous trip settings, and we usually recommend a 10% greater than that max fault in the process is the set point. Okay, now I referred to the recommendations or the guidance that were given by the National Electrical Code. And again, this is recommendations or general guidance as far as the type of curve selection used in relays. And for protecting transformers, the recommendation is to use very inverse shape as a general guideline. This particular chart is built into the NEC help system, but it's specifically from NEC 450.3a, which is NFPA 70. What this describes is for different size transformers and different impedance ratios for supervised and unsupervised, and they give us the max setting or ratio between full load current and the type of protective device we're utilizing. So for primary protection on a transformer over 600 volts, that is greater than 6% impedance, utilizing breaker protection, the max setting is recommended not to exceed 400% full times the full load current. Whereas if we're using fuse protection for the primary, recommendation is not to exceed 300. Now that doesn't mean we can't set it for something less based upon the demands of our system, but these are the general brackets that we need to follow. And then for secondary protection, over 600 volts and less than 600 volts for breakers or fuses, and the impedance levels. Again, it's a fairly confusing chart until you get into the details of the system. So hopefully we'll be able to kind of sort that out as we get into this. As I mentioned earlier, relays are the elements that tie the system together, and they do so with what are referred to as zones of protection or protection zones. And so you want to design your system such that the relay coverage is overlapping in these particular zones. So for instance, in this particular area of my system, I have both overcurrent protection in the primary, a differential relay for transformer protection primarily, and it will cover the zone between the physical locations of the CTs. So in this case, we have the primary protection set above the main breaker, and then the secondary CT below the main breaker going into our switchgear. If we were to relocate and put CTs on these outgoing feeders of the main, it would expand our zone of protection and give us some coverage or duplicate coverage in that physical part of our system. Likewise, there needs to be some overlap between the primary system and then the secondary zone, again, because we could have done something with the CT locations. Likewise, when we have feeders that have relay protection, we want to make sure those overlap. And again, you'll see how this effect is mapped out as we get into the considerations of doing the physical layout. So specifically on our primary transformer, we see that it's unsupervised, two-winding transformer. It's got an 8% impedance ratio. It's rated at 29.867 MVA. The primary full load current is 150 amps. Now we get that by taking the MVA, dividing by 1.732, and then by the voltage, and that'll give us the primary current, actually the primary current and the secondary current. So by those calculations, we get 150 amps on the primary. So according to the NEC table, the max set point for input protection would be 600 amps. And then the secondary current, full load current, is 1250. And the chart shows that we can go up to 250% coverage there, which would be 3,124. And then once we set up our relay, then we adjust the slope or the coverage of the curve to make sure we clear the knee in the TCC plot. Okay, with all that said, let's go to my TCC and see what it looks like. So we're talking about this section of my primary. I've already got that TCC set up. It looks something like this. So again, for overcurrent protection, we're going to be focusing on R18. And here's our transformer damage curve. Again, the thermal damage is the upper portion of the curve. The mechanical damage is the lower portion. We have R4 in here just for reference only. Clearly, it's going to be part of our zone coordination down below, and we'll deal with it specifically later. What we're focusing on is the coverage of R18. So if we look at this, we open up the dialog box for that relay, and we see that we have a CT and a high voltage breaker assigned for opening. And we had 150 amps for primary coverage. So let's say the minimum here is 160. So let's set that. That's roughly 10% above our FLA. And then we've got our very inverse setting. And we've just kind of plucked a time dial out of the ether. So let's make that 6. And then because we do have the ability to set an instantaneous current, and if we look at if we have a secondary fault, the maximum current into the transformer would be 1116 amps. 10% above that number would give us 1600. Actually, I want to set it a little bit lower. So let's make it 1200 and see how all this works. So as we make these changes, now we can see on my TCC curve, this tick mark at the top is the full load current for the transformer. And if you look down at the bottom part of my screen, it gives me the location of the cursor. And as I locate this mark for R18, it's showing me 1254 amps. Now wait a minute, Jim, I thought you said it was 150. What's going on? Well, when I drew the TCC curve, EasyPower picks out the lowest voltage in my particular selection, which is 13.8. Well, I'm really talking about the current in the 115 kilovolt range. So I'm going to right click on this upper bus and say set the reference for TCC scaling. Now when I go back and locate the transformer curve for R18, for my transformer TX1, I can see now I do have 150 amps down at the bottom of the screen. Then if I hover over the this green mark next to it is my pickup setting for relay 18. If I hover over that, it gives me an arrow that I can left click and drag. And right now it's set for 159. We set it for 160. And that controls this upper end of R18. It looks like a pretty good place to be. Now if I left click and drag, I want to make sure I'm clearing this particular need in the curve. And at the same time, now keep in mind the relay plots are showing us the reaction time of the relay itself. So we make sure we have enough clearance between any of these guideposts that we're looking to keep clear of. That includes the opening time of the breaker themselves. Now the breaker that we're using is BH1. And if we look at the data block for that, we can see that it has an opening time of 5 cycles. So 5 cycles is much less than a half a second. It's going to be relatively easy to keep within that distance at this upper end because we're in the multiple seconds range. So the bottom line is I'm clearing the knee. Now I want to talk about my instantaneous setting. And we set it for 1200 amps. Well, why isn't it showing up? Well, if I click in an open area and fault all the buses, I can see I in fact do have a 1200 amp setting for this particular breaker, instantaneous. And as I fault the main switch gear itself, because I have this breaker, this relay in the system, it's clipping at the 9,000 amps that's coming through the secondary of the transformer. So at that point, I feel comfortable with my instantaneous setting, set it at the 1200 amps. So what else do I want to say about this? Now, another question that comes to mind, and maybe someone is asking the question already, is normally when we talked about the transformer damage curves, we saw 2 curves, one for 100% damage and one that was derated for 58%. And if you recall, the need for that particular curve was for a single line to ground fault protection where we'd have a phase shift or a value shift of 58% between the primary phases and the secondary phase. Well, in this case, we have a resistance grounded secondary, so the current in a ground fault will be limited, I think in this case, to 400 amps, which is much too small to worry about as far as the offset of the 58%. So there's still a shift in the current phase to phase, but it's going to be so small that it's relatively insignificant as far as the dimensions and parameters of this particular plot. Yeah, another point I wanted to mention, if I come back here and fault all my buses, is that all my primary protection, and again, R4 is on the secondary, so I'm not even talking about it yet, needs to clear my inrush plot by at least 200%. So right now we show an inrush of 800 amps, and we've set this for 1200, so that's a 50% clearance. So let's give it a little bit more clearance just to make sure we're not sensitive to the inrush triggering. Okay, so I'm happy with this. Let's kind of go on to the next example. Yeah, by all means, if you got questions as we're going along, feel free to chime in. Okay, I think we covered everything I wanted to talk about here. Okay, so the next section is down below my main switchgear. I have a transformer, a second transformer to drop it from the 13.8 to 480, and then I have to deal with motor protection down below. So this transformer we're defining as unsupervised with a 6% ratio impedance, 1.2 MVA. We calculate the primary full load current of 53 amps, almost 54 amps. So 600% times that number according to the chart from NFPA 70 is 600%, which would give us 320 some odd. On the secondary side, our full load current calculates out to be 1549. And according to the chart, the maximum setting that we can use for a breaker is 125%. So that'll give us 1930 something. The motors are 250 horsepower. Full load current is 310 amps. The locked rotor multiplier is 6. So that gives us a locked rotor current of 1860. And then we've got a cable in here that's rated at 335 amps. And so let's see how we deal with this. So I'm going to close this. Let's go ahead and save the changes while we're here. And let's open up our motor description. Okay, so I mentioned earlier the transformer is important in this discussion, but the bottom line is going to be the clearances we have for our end load. And so we've already got, because we have the ratio between 2 to 1 between our two breakers, the feeder and the main, we have a good chance of getting coordination. And if we look at the plot, we can see that by adjusting this out to clear the current, the locked rotor current, we can get pretty good clearance from both the thermal damage curve and our the lower part of our breaker. Now again, I've faulted all the buses. So this shows us where our instantaneous setting is for the downstream breaker. Now we need to have clearance between, we have a clearance reference between the two breakers. I can display that by picking out both and then using the difference calculator. And that shows me I have 160 some odd millisecond between the two. Based upon my policy, I may want to make an adjustment to that. So and I'm also looking at what was for my secondary current protection is less than 1937 on a breaker. So let's go back and see what I've got going there. So I want this to be less than 1937. Looks like I've got 880. So we're in pretty good shape. And I may want to pull this over a little bit. All right, so the green, so that gives me good clearance between the two breakers for my motor protection, and I'm not violating any issues as far as secondary protection on the transformer. Now here I do have two parallel curves. 100% is the dotted line for the transformer damage, and then the solid curve, which is offset by the 58%, is the primary single line to ground. So I do need to be, because this is a hard grounded system, I do need to stay clear of this frequent fault area on my on my primary protection. So that brings me to the relay. The relay is this green curve, and it's here at the top, R6. And again, well, we can actually see it just looking at the chart. So here's my transformer full load current. We see it 1518. My relay's pickup is set for 62 amps, which gives me 10% above the 53.9. So, oh, we're on the primary side, so I'm looking at the wrong voltage again. I don't know if anybody caught that, but again, I'm looking at the bottom cursor as I look at these tick marks. So again, my full load current is 54 amps, looking at the cursor location at the bottom. So I want to set this pickup at 65. So let's keep it at 65. Now, my curve seems to be in the way as far as my coordination. So let's see what's going on there. I open up the dialog box, look at my settings for phase protection. I've got very inverse, and I've got a tap setting of 63.9, which we like. The time dial is out in left field. So let's resolve that with something a little bit more reasonable. And if we apply this, we can see we can pull the curve up. All right, so now I've got clearance between my breakers, my relay. I've got clearance of the curve of the knee. Now, what do I do about this lack of coverage or this equalizing out here? This goes back to my maximum current for a particular fault. So if I have a downstream fault, I can see that these breakers are clearing it before I reach that point in my primary. So my current through the, at least for a through fault, for the cable is being covered by the protection downstream. I'm pretty happy with these results. Anybody have an issue with that? There's no gap between the relays. This is a long time, curve stops. Yeah, I think I'm cool with this. And again, here we have the instantaneous disabled because we have that feature built into my downstream breaker. Okay, let's see if we got, this actually shows it better. If I have a fault on the secondary of the transformer, I have clipping on my primary protection. So what happens if I get a fault here? Fault the node. Yeah, I'm thinking I might have some problems with the cable and a fault there. That'd be something I'd want to look into. Okay, again, there may be some areas that I'm not covering necessarily in detail. I'm trying to just cover the big picture with the settings on the tools. Okay, let's jump back into bigger picture. All right, any questions with that? Now, we referred to neutral resistant grounding during the poll questions. This is an area where it used to be, years ago, there seemed to be a lot of systems that were utilizing neutral grounding on the transformers. And because there were some obscuring or limitations of some current operations in those times, it kind of fell out of favor. But there are some strong elements towards recommending the use of NRG in new designs, because you can get better protection, for one thing, against arc flashover. High majority of faults, of system faults, start off as ground faults, and it's recorded that frequently ground fault to single phase can be elevated into a three-phase fault in an arcing event because of that high current in a hard grounded system. So by limiting the current in an arc, the ground fault, gives us better protection against arc flash, although it's a little tough to quantify. It does increase personal safety because the limit on an accidental grounding will be limited to some lesser value. It does make it easier to locate a first ground fault in our system if we're running clean. It does permit coordinated protective devices in the ground system. And depending upon those settings, it does allow continued operation as long as the first ground can isolate a particular load. So let's see how this is kind of shown in my examples here. I'm going to close this puppy out. And open up our utility ground. So in this particular system, we're using, I believe it's a 400 amp neutral ground on the primary, on the main transformer, on the secondary side. And the way that appears in EasyPower is if I go into the transformer dialog box under the impedance tab, I can indicate the amount of impedance I'm using or the amperage class of that protection resistor, and then the tool will calculate the other element for me. Now that gives me the ability to look at the protection afforded by my ground setting. So I have a neutral leg ground over phase current detector. I have zero sequence protection or relays downstream of both of my breakers. Now, first of all, we're looking at phase current, so this doesn't mean much. What I need to do is invoke a single line to ground fault, and then specifically look at my ground coordination. And as I do, I look at the following setup. So we have, let's look at these individually. Here's my relay R6, which looks like it ought to be this puppy right here. It's red, yeah. So right now it's set for 100 amps, which is 25% of the rating. So we want it to trip slower than our 400 amp limit. Now the maximum setting for a 400 amp fault would be, we want it to clear within 10 seconds, which would be the rating on our resistor, our grounding resistor. So the relay that's set here, R4, is not showing up. So let's give us settings for R4. Okay, first of all, the ground settings are set up 2. So function ID 2. So we show it a fixed time. Let's go ahead and set it at close to 400 amps. And let's, for just general purposes, set it up for a couple seconds. See how that looks. And so there's our 4, and I don't see it. Well, let's bring it down a little bit and see if I can find it. Okay, for starters, I see a little bit of an issue here. We have our CT set up for 200 to 5, but for some reason the setup for the relay is set up for 1200 to 5. So let's see what's going on here. And the issue ends up being we're using CT5, but we've got CT4 selected. So let's correct that error. Let's go back to our settings. Now we got a 200 to 5 ratio. Let's make it a little bit more aggressive than that. Now we should be able to find it. There it is. So it's a green, it's a color coordinated green. So again, we've got it set up to trip at 2 seconds at 108 amps. If we want to range that up to 10 seconds, we can set the limit there. Let's say there's no need to set it that high. So in our design preference, let's set it up for a 2-second limit and cover a range from, looks like 150 up to 10, the full 400 amps. Then that allows me to coordinate downstream on R6 and likewise on R7. So at this point, if we had a fault on this bus, we would get a trip on R7 first, and then R4 would serve as backup. So at this point, we have a ground fault coordination, and we're limiting a ground fault to a maximum of 400 amps. So at that point, now how do we quantify this just change in arc flash? We don't, because the arc created less often from a single ground fault, but it could be generated by a 3-phase fault or an arcing fault in the insulation. Point being, this does have some secondary benefits in arc flash, potentially less frequent than if we had a hard grounded system. Okay, so let's save this one. Seems like I had another one. And it gives us the ability to coordinate downstream loads. So the same kind of thing, we have R9, we're looking at a single ground default, a single fault. We're looking at the ground coordination. And if we have a fault here, where's R9? So we got the right one. Let's make sure I'm looking at the right one. All right, phase over current. Let's see if I can find it this time. Yeah, so there we have coordination between the load and the ground current for the transformer itself. So it seems like it's something that would be relatively easy to quantify cost-wise versus the impact on the system. Chuck's asking a good question. If you have a soft starter on a VFD motor, how's the startup curve changed? That's outside this. It's something we tried to cover previously, and I don't have. Let me see if I have an example. That's a good question. Yes. Let me kind of go. Chuck, that's a real good question. I wish I'd come up with it as an example to start this discussion. So let me kind of finish this, and I'll go back and see if I have a chance to catch it. So that covers my refiner. I can't spell. Okay, so then an arc sensing relay and a differential relay both can determine a protection zone based upon the physical placement of the sensors. So we already mentioned that the differential is based upon where the CTs are located. I can expand that zone by putting the CTs on the feeders down here below and include this particular part of the switchgear in terms of protection. Likewise, if we were utilizing a flash sensing relay, wherever we put the sensors, the arc light sensors for picking up, would expand the zone of protection there. So let's kind of look at how this is set up in EasyPower. Looks like I overstayed my welcome on that TCC curve. So let's start over. All right, so again, both the arc and the performance of the differential relay cannot be simulated by a short circuit analysis, which is what our curves are being used to predict the performance. So the way this is handled in EasyPower is to have a time element that is measured by the manufacturer's response, both for the relay and the pickup settings and the breakers that the particular relay is going to trip. And so that's covered in when we go to the database edit setup for the switchgear that's being protected by that particular relay. So for starters, this relay is going to trip BH1, and so ultimately it's going to protect this relay. If we have an arc sensor, the same thing is true. It's going to be connected to one of the or both of these breakers, and that trip time or the opening time for the breaker needs to be included in the time element. The time element is set up in our arc flash hazard tab, and rather than just focus on the calculated response time of any protective device, we'd also want to look at user-defined time. And so let's say we had a differential relay upstream would be R17. And according to, let's say it's a differential relay, so it's a 87. And according to the manufacturer and the setup time for the relay, response time, and then the opening time of the breaker, we had a response of 0.095. And let's say, just for grins, if we're in the same area, if that relay in fact was an arc sensing relay, and it had a response time of, let's say, something quicker, then the tool will give us what the effect of that protection is. So now as we kind of close this set point, go into short circuit, this response time will not show up on the coordination curves, but it will show up on our calculation for a short circuit arc, or short circuit fault rather. As I fault that bus, I can arrange for arc flash, and now the tool shows me that for an arc on that, for a fault on that bus that was differential, it would give me a protection of 0.095, and the resulting instant energy would be quite a bit less than in normal operations. Now, one would ask, why didn't it show me the arc? And so let's see if I can go back and figure that out. I think when I have two overlapping let's see if I take this one out, if it works for me. So again, back to short circuit, fault this bus, look at arrange for arc flash. Okay, so we're learning something here together. It's not going to show me the other unless I select other. Yeah, so user-defined devices. So I need to put this up in the first. It won't allow me to use multiple trips to the one upstream device. Let's make sure this works. Okay, one more time. Short circuit, fault that bus. Now you can see it's showing me both the response time of the upstream relay R18 on overcurrent, but then it's also including the response time of that other device. And if I wanted to label it for maintenance operations, I could generate that as part of my instruction for maintenance. I wouldn't label that for, personally, I wouldn't label it for on the equipment door itself. That I digress. Al, you're asking a good question. The question is, how does Smart PDC deal with this? It can't deal with. Smart PDC uses the National Electrical Code rules to make the settings for the timing elements. It can't deal with differential or arc flash. Now, with that said, let's go into coordination. Let me open up one of these TCC curves. And if I invoke Smart PDC, well, it works on, I was pretty close on my ground current. Let's look at one for, in fact, that brings me to the last example, and that is my transformer with multiple panels. So here I have a fuse protection of a breaker and then two subsequent breakers below, protected by multi-case circuit breakers. No way are you going to be able to get perfect coordination from any of the above elements. The point that I was trying to make is not only how much interaction we have, but as I fault each individual bus, it'll show me that in fact I do get some amount of coordination, although it's going to be countermanded by the instant energy that's going to be created. But this is showing me that potentially this breaker, which is where panel 1 row 7 will trip, and then the second to trip will be panel 1 main, which is kind of the coordination we'd want. Now, the point that is asked is, will Smart PDC take care of this? it's going to throw up its hands on multi-case circuit breakers, but it will give me some potential results for the relays. In fact, it's a very good first order approximation for the relays. Specifically, if I bring this back to what it was, it's showing me what it would recommend for R4 in the course of this analysis. And so the starting point and the thing that I would use Smart PDC for is the report that's going to be generated as a result. And the areas where I'm having issues for protection based upon the fact that we're using a multi-case circuit breaker. So yes, Smart PDC is extremely valuable in these situations. Now, one more thing I wanted to point out. So this was the fuse protected. The fuse is this big red glob here, and it does a pretty good job of protecting the upstream transformer, which is its primary function. And again, you can see not all of the transformer gets protected except by the fact that its overlying levels of protection below it. So with multi-case circuit breakers, you have my condolences. Okay, one other thing I wanted to talk about. We touched on this, and it was difficult with multi-case circuit breakers. Built into EasyPower are a couple features that are worth talking about. One is the results from manufacturer test results, which are charts in the device library that shows correlations or guaranteed by test coordination between an upstream device and a downstream device. And so when I have a situation like this, it's the saying, if I have a I-line HD smart square D breaker rated for 150 amps upstream, then I can use a standard EDB downstream, and I'll have correlation up to 1300 amps. So how that looks is illustrated by this example. And I appreciate some of the questions that are coming up. We'll actually have to focus on them in another time. All right, so here's my two breakers. You can see I have 150 amp I-line rated at 35,000 amps, set for 150 trip, and then a downstream set for 70. And according to that chart, they will coordinate up to 1300 amps. How this is going to appear on my coordination chart, or my coordination TCC plot, is thusly. If we kind of expand this a little bit, it shows us a tick mark, and this I'll show you where this is enabled. It shows a tick mark that says per manufacturer, BL1 and BL2 will coordinate up to 1300 amps as long as BL1 instantaneous is off or max. Right now it's set at max, and if I fault this downstream bus, it's less than 1300 amps, and so the manufacturer guarantees that BL2 will trip first and will coordinate with BL1. So it has some limitations, but it's the recommendation on multi-case circuit breakers. Yeah. And the last thing I wanted to show or bring up, even with the example of the even with the example of multi-case circuit breakers, I can utilize a feature called sequence of events to capture relative trip performance, even in a complex system. So if I'm in a single bus fault looking at current in coordination, single bus looking at current, and fault this bus, let's fault this downstream panel. The tool makes available to me the sequence of events icon and then shows me the chronological tripping time of the upstream devices. Now on the one line, it's not going to show the breakers because they're in the schedule for the panels. But this is showing a red on this fuse tripping at 3+ seconds and a red on this breaker which don't trip at all, which indicates that this low current, I'm depending on the downstream devices. How I get deeper into this is I go into my PDC options, create a sequence of events report, and if I've done that and I fault the bus again, then under my list of windows will be shown a sequence of events report. And now it shows for a bus on panel 1, for a fault on panel 1, I get trip times and I have coordination issues with the main on panel 1, but then I do have backup from my fuse. In fact, the fuse may even have blown prior to that, 20 seconds prior. So if I can't change the main on the panel 1, I may have luck with the feeder on the upstream side of the other panel. So again, this will give me a clue, and it's useful for looking at all parts of my system. So if I pick out this downstream load, fault the bus, look at sequence of events, I can see this breaker trips at 1/2 second. This breaker trips at 3/4 second. This breaker trips at 1.7 seconds. And then this breaker trips at 3.18 seconds. And again, it's showing coordination. And that'll be also reflected on my report. Okay, so we covered a bunch of ground. A lot of good questions. And unfortunately, I don't have time to answer them at this point. I will do a Q&A response via email. And I think you've given me some good ideas for future webinars. Appreciate everyone attending today. By all means, check out the website. If you don't already, make sure you sign up for the newsletter. There's a lot of changes going on, not the least of which is an EasyPower update that's just been released in the last week. And we do appreciate you supporting EasyPower. Have a good day.